Hello, we are Lower Moreland High School and our project is WAFIS, which stands for Water Filtration of Flooding and Extraction of Stormwater. If you live anywhere in Pennsylvania today, you are undoubtedly no stranger to flash flooding, which is a frequent occurrence in our state and one that has caused much harm. In fact, flooding is the most common and damaging natural hazard that occurs in our state, and Pennsylvania ranks as the second most flooded state behind Florida, which is a peninsula. The reason we get so much flooding is because of our intense precipitation levels, and even when rainstorms are short-lived, the sheer amount of rainwater, combined with the imperviousness of our roads and the overflowing of storm drains, can commonly become a recipe for flash floods. Our county of Lower Moreland has experienced this many times, and despite its often short-term effects, flooding still makes roads dangerous for driving.
Rapid urbanization has led to numerous challenges, including increased water pollution and a result of higher risk of flash flooding due to impervious surfaces. Traditional stormwater management systems often fall short in addressing both environmental and infrastructure concerns. Our project responds to this by proposing a novel water filtration system that not only prevents pollution from seeping into the ground, but also enhances the ground's ability to absorb water, mitigating the impact of flash floods. The innovative design draws inspiration from the layered structures beneath permeable surfaces commonly used in urban infrastructure. To learn more about how we could address this issue, we reached out to Kevin Conahan, a senior traffic project manager at ACOM, who has worked with PennDOT on roadway design and maintenance, including projects that involve stormwater drainage systems. In our discussions, Mr. Conahan brought up some very important points, such as that one of the main reasons that roads are not able to absorb water is that the pavement and clay soil, which is often buried underneath it, does not absorb water particularly well compared to materials like sand or gravel. Another thing Mr. Conahan informed us about is that PennDOT does not widely use porous asphalt or other permeable materials designed to address pollution on the roads. However, he was able to offer advice in constructing roads to mimic the design of materials laid underneath roadways. He described how when laying down layers of sediments before depositing pavement, larger aggregates are often poured underneath finer materials like sand in order to provide support and level out the roadway. He also told us that when layering these aggregates, often synthetic net-like fabrics are wrapped around each individual layer to keep them in place. This is important because, as we soon discovered, when smaller materials intermingle with larger materials, it creates ruts and holes in the top of the road and loses structural integrity.
So the design of our water filter prototype consists of a clear plastic pot with strategically layered materials, each chosen for its unique filtration and absorption properties. A net-like fabric at the base of the pot prevents the materials from falling through, which ensures stability and prevention of the filter materials escaping. The layering sequence includes marble chips, pebbles, mini marble chips, limestone pellets, leveling sand, regular sand, and activated carbon. This combination of materials serves as a multifunctional filter capable of removing particulates, adjusting pH levels, and reducing metal content in the water that's filtered through. These selected materials in our water filtration system contribute to filtering water by taking advantage of their unique properties. The marble chips, for example, play a crucial role in adjusting the pH of the water, which helps to neutralize acidity and create a more balanced environment. Pebbles and mini marble chips primarily aid in the mechanical filtration process, acting as barriers to larger particles and sediments. Limestone pellets contribute to ion exchange by reducing the concentration of metal ions in the water through absorption. Meanwhile, the leveling sand and regular sand layers further clean the water by trapping smaller particles and impurities, providing both mechanical and chemical filtration, while activated carbon and charcoal use absorption, removing organic contaminants, odors, and residual chlorine from the water, in addition to being a disinfectant. The cumulative effect of these materials provides a comprehensive water treatment process that alters the pH levels, metal content, and particulate concentration, along with microbial contaminants, resulting in improved water quality that can be used for various applications.
Our design process involved first gaining a comprehensive understanding of the properties of each material and their interactions when it came to filtering. After selecting our materials based on these properties, we then attempted to optimize the arrangement, considering factors such as particle size, porosity, and chemical reactivity to design our first prototype. Testing was conducted with various water samples, measuring the pH, metal content, and particulate concentration before and after filtration. Iterative improvements were made based on these results, leading to an optimized design that provided the best possible filtration. One problem that we shortly ran into was the infiltration rate of the water. Since one of our goals was to increase the groundwater absorbance in certain areas by replacing impervious materials with our porous layers, we also had to prioritize the speed at which the water was able to pass through the filter layers. This conflicted with our goal of filtering water because the filtration ended up being most effective when layers were ordered from top to bottom in increasing particle size. But the water was absorbed by the material nearly twice as fast when the larger materials were on top, since the larger gaps allowed more water through than the smaller gaps. We also realized that having larger materials on the top that meant that other substances in the water like leaves, rocks, and large chunks of dirt would be filtered out first, preventing them from clogging up the lower, more fine layers.
As you can see here, the costs for each of our 7 materials were measured in dollars per cubic foot, and the sum of these estimates was a total of $32.66. Extrapolating this to a square mile with a depth of 1 foot, the materials end up summing to $172,444.80. This total, combined with the extra costs it would take to install pipelines to divert the water collected from our filters to nearby water sources, such as streams or reservoirs, would comprise the entirety of the cost of materials of this project.